So in the last video, we saw about how processes are created by using the fork system call. So this time, let's take a look about how processes are destroyed, or rather, what we need to do as programmers if we're dealing with processes that are going to terminate or going to end. Um, and this is called, to be a little bit colorful, reaping the process. Uh, the idea, I suppose, is that you're waiting for this process to die and coming in as the Grim Reaper and taking its soul away. Where the soul is actually some information about the process, particularly its exit status. What happened to make that process terminate? Um, so when a process calls exit or returns from main or so on, that terminates the process. The process is no longer running, but it's still kind of there. In operating system tables with a list of the process, for example, this is one of the internal data structures of the kernel, that process is still going to be there. It's still going to have a process ID, meaning that process ID can't be reused. We could eventually run out if our system is running long enough. Um, Also, each process has that exit status, and if when a process terminated, it just went away completely, then what would happen to the exit status? It would go away. And if we want to be able to see what happened to a process that we started, for example, if we're the shell and we want to be able to report that the process terminated successfully, or maybe not report anything in that case, or print a message saying the program terminated because of a segmentation fault, which you have seen from the shell, I'm sure. Um, so in order to get that information, the shell has to be able to find the exit status of this process that is already terminated. So the operating system, in some of those tables that it keeps around about processes, has that process's exit status. So if a process exits and it's still kind of around and we weren't able to do anything about that, then we would eventually run out of system resources. So we have a way called reaping to get that process out of the table, and while we're doing so, also find out what its exit status was. So reaping is done with one of two functions. There are a few other related but non-standard functions that can be used as well, but these are the most common ones, wait and wait PID. So these are called by the parent. Remember, every process that's created is created with this fork system call, so there is a parent and there is a child. So when after the child terminates, if the parent calls wait or wait PID, that will return some information about the process, its exit status in particular, and also an indication of whether it was exiting because of normal termination, exit in a program, or because it received a signal. So when our process terminates, the parent calls wait PID, gets that information. Also, you might think, why is it called wait? Well, if the parent calls wait or wait PID and the child hasn't terminated yet, then it will do exactly what it says and wait for that to happen. And once that happens, once the parent is given the exit status information, that's really the main reason we're still keeping the process around. Well, then we can get rid of the process. The kernel gets rid of the process from the various tables. Its process ID is now available to be used by some new process that gets started up. And its exit status is no longer stored, at least not in the kernel. The parent hopefully stored that in a variable somewhere. So if you have a parent process that creates a child and you don't reap the child, well, in many cases, that's not a terrible thing, because when the parent terminates, the child is reparented. Every process has to have a parent process. If your parent process terminates, the kernel changes your parent process to be a particular process init, which has the process ID 1. It's the program that starts up when the system first boots. So that means if your process wasn't running for a very long time, if the parent process isn't running for a very long time, then then the child is going to be eventually reaped by that init process, and well, we don't have to worry about it anymore. But if you have a parent process that's long running, it's going to create many child processes and isn't going to exit anytime soon, then those child processes are going to remain zombies unless you wait for them. So a program that's intended to run a long time and possibly create a lot of child processes, something like a shell, for example, that you're typing your commands into. Every command you type, everything you run goes into at least one and maybe more child processes. And in those child processes, we need to or when those child processes exit, we really want to reap them. Not only so we know the exit status, but because if this shell is running for a really long time, that could be a lot of zombies. Also, servers. Servers are intended to run for a really long time, and we'll see in a later chapter, one of the common ways servers are implemented is every time a connection comes in, they start up a new child process to handle that connection. Well, that connection is going to end eventually, that child process is going to terminate, but our server is still there, so it won't be reparented to init. It's going to stay a zombie unless our uh, main server process eventually waits for those child processes. So there's an example in the slides about a zombie process, but let me show you this on my virtual machine. So this is in the lecture 13 code. We have the make file as usual, a README describing what's here, the CSAPP, those are the initials of the textbook, the file of helper functions, and the header file to go along with that. We have this fork.c. That's the example we saw before. That simply forks and then prints one message in the child process, a different message in the parent process. And then another program called forks.c, which has a lot of different things related to forking, a lot of different ways you can call fork. And we've seen some of these as examples, but I want to look now at fork 7. So here we have a process, or we have a function fork7. It's going to fork. Remember, if fork returns 0, that means we're in the child process. In the child process, it's going to just print a message and exit right away. Else, in the parent process, we're going to print another message and then go into an infinite while loop. So that means the child has terminated, the parent will still be running, and we'll see what happens when we do that. Now, if I want to be able to see this process, run the ps command, for example, I need to still be able to run things while it's running. So I'm going to run it in the background. And I'll show you how to do that from the command line. So to call this fork7 function, we call we run the program, which checks command line arguments, converts the first command line argument into an integer, and then based on what that integer is, calls one of the functions. So if we want to call /forks space 7. So let's make I had a leftover header file or a leftover object file from an earlier virtual machine, so I'll need to delete that. Make, okay, forks 7. Now, if I run it like this, then, well, I don't have my shell. I'm not getting back to it because the program's still running. The shell, in fact, is calling that wait system call to wait for its child process, forks, to terminate. So let me control C it. So now, if I do PS, I don't see the parent or the child. I terminated the parent. The child was a zombie, but it's been reparented to init, and it reaped it. So let me run it in the background. So ampersand at the end of command line runs that command in the background. And I can press enter to get my prompt back. So the parent is still running right now. And if I do a PS, I can see I have two processes here. Forks 14870 as the process ID. Well, I can see up here that was the process ID of the parent. And 14871, that's our child process ID. It's right here. It is also forks. Well, that kind of makes sense. We made a clone of the process by calling the fork system call. That clone is going to have the same name as the original. But it also says in angle brackets, defunct, dead, gone. This process is a zombie. So it's not running, it's not taking up very much memory, but it is taking up a little because of those slots in the operating system tables. So in order to end that, I need to kill my parent process. I can press FG to bring my background process back to the foreground, Control C the parent, and now if I do PS, the parent has terminated and been reaped by the shell. And also, the child process has it already terminated, but it has gone away. It's no longer in the output of PS because when the parent died, the child's parent was made init, and init just sits in a loop waiting for a process to die or one of its child processes to die. All right, so let's take a look at another example. So fork 8 is one where the child process prints a message, it goes into a while loop, and the parent process terminates immediately. So if we run this, forks 8, I'm going to run it in the foreground. Remember, the parent is in the foreground. The parent is the thing that the shell is waiting for. So running the child has a process ID 28323. The parent has process ID 28322. Also, you notice I got my prompt here. Sorry, up to here. And then the message from the child process printed. Well, the order in which those things happen, as we saw before, is indeterminate. The child could run before the parent, or it could run after the parent has had a chance to run a little bit more. And because of that, what happened is the parent process exited. Bash, my shell, which was waiting for that process to exit, saw that it did, printed my prompt again, and then the child process printed its message. And the child process is still sitting in a loop right now. I can press enter to get my prompt back. It's not that I wasn't at the prompt, it's just that I got this message while I was there. If I run PS, I can see my parent process, 28322, is gone. It has terminated, and Bash waited for it, so it's not a zombie either. And my child process, 28323, is still here, and it's not a zombie. It's not listed as defunct. It's still running. While I can't bring it back to the foreground, it is effectively kind of in the background at this point. But I can't bring it back to the foreground because, well, the shell doesn't know that it's there. The shell thinks that this process terminated because it did. It doesn't know that it created a child process. By the way, if you're thinking, well, I could do something with that and start a program and have it continue running even after I log out, that's exactly how servers work. So anyway, let's see what we can do about this, because I don't want this program to keep running forever. If it were just sitting there paused, that would be one thing. I still wouldn't want it running forever, but it wouldn't be taking up too many resources. But if I run top, that's the program I talked about a little bit ago, by default, it's sorting by percent CPU, and that program is sitting in a while loop, spinning, just repeating the loop, incrementing its integer over and over again. Actually, no, it doesn't have an integer. Just spinning in the loop over and over again, doing nothing. And, well, that's taking a lot of CPU. So, I'd better terminate the process. And the way I do that is with the kill command. Kill, and then the process ID, 28323. And now that process is gone. So let's take a look at that, or those couple of system calls for reaping child processes. So wait is the first one. Wait, it takes an integer pointer. That's a little bit weird. It returns an int. So it pauses the current process, the one that calls wait, until one of its children terminates. So we're not specifying which child we want to wait for. If we've created several child processes, this will just wait for whichever one is the next to terminate. Then when it terminates, well, we've got a couple of things we want to know. We remember that we waited for any of our child processes, so it's probably a good idea to know which one it was that terminated. For example, in a shell, we want, if it's a background process that terminates, we don't necessarily need to do the same things as if it's a foreground process that terminates. So that's the process ID, but remember one of the reasons we needed to reap a process, the whole reason it's being kept around, is so we can find its exit status even after it's terminated. Well, we can't have two return values in C or C++. So in C++, the way we would handle that, we want to have two outputs, but only have room for one return value, would be to pass an argument by reference, make it an out parameter. Well, in C we don't have references, but pointers are pretty similar. So here we're taking a pointer, so we have to pass in the address of some integer variable, and wait, besides returning the process ID, will also write the exit status of the process to that integer value. Somewhere inside wait, there's a line of code that looks like star child status equals something. So in order to wait for a process, we could do this. By the way, all things might have errors, so we'll take a look at some of the error nodes that are available for it. If you pass in a null pointer for the child status, meaning you're not giving it an integer, or a pointer to an integer, then wait just won't store the child status. It'll throw it away. You'll still find the process ID. So that child status isn't just the exit status of the process, not just the number you pass to exit or the number you return from main. Instead, it is a kind of bit field with a bit indicating whether it was normally terminated or abnormally terminated, and then the rest of the integer is used to store the precise exit status or the precise reason that it abnormally terminated. So in order to get those individual bits out, rather than writing a bunch of bit manipulation code yourself, you can use some macros that are defined in wait.h. So you use these like function, w if exited, parentheses, and then you give not the pointer, but the integer that it points to, and then it will return true if it exited normally, false if it was abnormally terminated. W exit status, if it was terminated normally, that gets the exit status out of that integer. And the same thing for signaled, which is abnormally terminated. Was it signaled, and what was the number of the signal that terminated it? Also, a process can be stopped For example, if we press Control Z when we're running a program to put it into the background, or rather to suspend it, it is stopped until we either bring it back to the foreground or put it in the background. W stop sig, which signal caused it to stop, and W if continued, which is when you continue a process that has been stopped. So you can see more about what these mean either in the textbook or in the best place to look for information about functions, the manual page. So man wait will show us what we saw before. You notice on our Linux system, it's actually not returning int, but a PIDT. So that's probably a better way to do it. On older Unix systems, it was int. You'll notice there are a couple of header files we need, systypes.h for PIDT and so on, and syswait.h for the functions themselves. And you can read more about how these work. There are some options that you can give not to wait, but to some of these other functions, explanations for what those macros mean and how they're used. There's also information about the return status. Wait could return an error, so it could return -1 instead of a process ID. And here are the possible errors. This is what error no might be set to. eChild, if there aren't any child processes. For wait PID, eChild, if that process doesn't exist. We'll see wait PID in a minute. eEnter if something happened. We'll see more about that in a later chapter of the book. eInval if we passed in some invalid options. So let's take a look at the other function besides wait, which is wait PID. So this lets us, instead of just waiting for any of our child processes to terminate, wait for a particular one. Now, if there are other child processes running and they terminate, but we're still waiting for this other one, they're going to be zombies temporarily. So wait PID, if we do have multiple child processes, we have to be careful about using it so that we're not waiting forever for one child while there are other ones we should be waiting for. So we give it the process ID of the child we want to wait for, the same pointer to an integer parameter for the status, and some options. This is a bit mask made up of a bunch of macros you can read about in the manual page. We OR them together with bitwise OR, vertical bar, to select the ones we need. So here's an example of wait PID. This process runs, or this function, n times whatever n is defined as. It will start a child process. In the child process, it will exit with a particular status. So going from 100 up to 100 plus n minus 1. Then the parent process will, in reverse order, wait for the child processes by calling wait PID on that child process, storing the child status, passing no particular options. If the child exited normally, so that's that W if exited macro, then we'll get the exit status by calling W exit status on the child status integer, and we'll print a message to that effect. The child with that PID terminated with a particular status, which should be one of these numbers. But if one of the children wasn't exited, that means it must have terminated abnormally because we didn't ask for any options that would let us get one of those other things we saw. So we'll just print a message saying it terminated abnormally and give the process ID. We could get the signal number, but there's no point doing that right now. We'll see more about signals later, though, and what we can do with that. All right, so one more function I wanted to talk about is how do we actually run other programs? Because fork, the way we create new processes, doesn't actually run anything else. It's the same process. It's a clone of what was running. So we somehow have to have some way of having a process run different code from what it was running before. And the way we do that is with execve. So there are actually lots of different functions in the exec family. If I type man exec, I'll get a list of several of them. You'll notice exec VE is not listed here. You'll also notice this is in section 3 of the manual. Section 3 is library functions. So these are all wrappers around the one underlying way to execute other things, which is exec VE. The VE stands for vector, which really here means array. It takes an array of pointers to strings as the command line arguments that it's going to execute. And the E means you can also pass it an environment, which is this thing. So execve will take the file name you give it and try to execute it. Now, it does have to be an executable file, not necessarily the kind that you get out of GCC, the ELF executables, but it has to be marked as executable in its permissions. So you can chmod chmod plus x, then the file name, to make it executable from the command line. But it takes the name of a file, which had better be executable. If it is a object file, specifically an executable object file, the kind of thing we get from GCC, then it will run it, load it into the appropriate places in memory, or set up those memory maps as we saw in the virtual memory chapter, and then start executing its code. Or the file could be a script. It can have a line starting with pound exclamation mark. And if that's the case, it will run whatever comes after the exclamation mark and pass it the name of the script file as an argument, which is exactly how we run scripts. So if you've ever made a shell script, you start with a line like this, then and make it executable. When you run it, execve will actually execute bash, the shell, and pass it that script as a command line argument, and the shell will run the script. You can give the list of command line arguments. Remember, if you remember how command line arguments work in main, it's the same idea here. The first command line argument that we pass is actually in element 1. Element 0 is the name of the program we execute. By convention, that's the same as the file name. We can make it different. If it's different, we're still going to execute that file, but we're going to tell the process it has a different name. Some processes or some programs will make use of that, so you can have one program that does several different things depending on how you call it. We can also pass in environment variables as another array of pointers to strings. By the way, both of these arrays need to be terminated with a null pointer. They are both arrays of string pointers. The size isn't specified, so we need a null pointer at the end so that execv or whatever other functions end up dealing with them know where they end. Environment variables are things like name equals value, like user equals your username, or path equals the list of directories that that the shell or execve is going to search for, and so on. So we might see a little bit more about environment variables later. So execve overwrites the existing process with the stuff that was specified in that executable file, whether it's this one or the one it got from the interpreter line. So it overwrites all of the process's code. It overwrites all of the process's data and also the process's stack. When I say overwrites, that's actually probably a lie. Most of the time, it will just unmap the ones that are already there, remove them from the virtual memory mapping, and map in completely new things. The code from the executable file, the data segment from the executable file, and then a stack that's mapped anonymously. The child process, or not the child process, but the newly running program will have the same process ID. This is the same process running different code now. Also, any files we open will still be open in the child process. This is not always exactly what we want. Sometimes, though, that's useful. In particular, if we open a new file and put it on file descriptor 0 or 1 or 2, the standard file descriptors, then we're changing where that child process's standard input or standard output or standard error is going. And, well, that can be useful. In fact, that's how the shell does redirection. And if you take a look at Lab 3, you'll see a little bit about that. Also, signal context, which is something that we'll talk about later. So execve, you call it, and it never returns. So it's kind of like exit in that respect, but it's not terminating the process. Instead, it's replacing your code, the only place it would have to return to, with completely new code. There is actually one case where it can return, which is if there was an error. So if you call execve, usually right after that, you would have a call to p-error or something like that to print an error message, and then a call to exit. Maybe if you weren't able to execute it, you might have a fallback, so you would have something more complicated. But after execve, the line of code that follows that is an exceptional case, only when the program couldn't be executed. If you look at the manual page for execve, you can see some of the reasons it might fail. E-access, we might not have access to the file, or it might not be the kind of thing we could execute, or it might not have executable permission. We might see e-fault if that argv vector or that env vector we passed in was pointing off to random invalid addresses, and so on and so on and so on. All right, so with fork and exec then, you can create processes and have them do new stuff. So I would suggest taking a look at Lab 3. It's not due until sometime next week, but I would suggest go ahead and look at that and read up a little bit in the chapters in the textbook on how processes are created, how redirection works. That lab has you implement something that does a redirection and then calls an external program. Now remember, execve replaces the process. Typically, when we're writing a program to call other ones, that's not what we want. We want to call another program and then when it's finished, do something, or while it's running, do something. Meaning, usually when we use execve, we're going to be pairing it with fork. And in that assignment, you'll see a little bit about that. So I'll be back before too long with some videos about signals. Until then, see you around.